This is a bit of an odd talk for me because I really took the messy research statement to heart. And what you were looking at is what I affectionately call airplane slides. And I also had a Bloody Mary on the flight. So we'll see how this goes. Um, yeah, I'll not give too many disclaimers. I'll just jump in and yeah. All right. So I'm working on a project called Wetware with a handful of other people. It's an open source secure execution environment for off-chain distributed applications. It runs in TEs too, and kind of its big thing. I'm not going to get very far into this, but the big thing with Wetware is this sort of secure composition problem that Dan has been talking about. So um, let's sort of jump in. We're at a conference called NoConsensus. So we're all building distributed systems. I would argue most of these are peer-to-peer systems. And we're sort of doing it like it's 1999. What I mean by that is a couple things. First of all, a lot of what I've seen kind of in practice is people setting up REST endpoints in various different machines and various different networks and calling it a day. So it feels very turn of the century. And also, it turns out that back in 1999, they were actually doing this in some ways better than we are now. They had like very good, robust, secure, and track proven protocols for solving some of these problems. So the intent here is to kind of just take a random walk, meander through some of this design space, and please don't look for any sort of well-partitioned idea in this. We're just going to vibe it, and I'm going to sort of tell you what the flavor and the sort of everyday experience of this looks like, and point to a couple of different paradigms that I find very kind of stimulating for working in this environment. And hopefully by the end of this, in the 8 minutes I have remaining, I can show you how hopefully some of this converges into a hopefully well-behaved system that we can build really robust off-chain composable services with. All right, so this is one such example of don't look for a well-partitioned idea. Hopefully this should be kind of obvious to everybody that composing or indeed writing any kind of off-chain service is a tricky thing. And it's mostly tricky because of the guarantees we give up when we leave the blockchain. And the big one there is concurrency. And concurrency is this kind of special thing because it's actually the flip side of a lot of coins, like correctness, like security, in some cases even like performance. And so there's a turn of phrase in Mark Miller's work that I like a lot, which is he talks about this destructive interference from programs that have too many degrees of freedom. And I like this because it gets us thinking kind of what I think is the right track, is just we need to specify our programs so that they can do fewer things, but we need to do this in a way that we give up as little performance as we can get and retain sort of the other properties that we desire. Yeah, so here's an example of airplane slides, right? This is a piece of cardboard I had in my bag. What I want to illustrate with this piece of cardboard is a really common kind of motivating example that I see everywhere. So here you have three like computational processes, Alice, Bob, and Carol, and they're set up in some loose pipeline where you have a sort of feed-forward system where you're passing messages from one to the other. And if you approach something like a permission system naively, then what you're tempted to do is call out to some oracle in the environment at every step and essentially ask, am I allowed to do that? And there's two things I want to, actually four things I want to point out here. The first one is that this, from a performance point of view, this is going to stall any sort of pipeline optimization you have with RTTs that are essentially leaving the flow of application programming, which is the pipeline going through Alice, Bob, and Carol. And it's going to call out into this oracle and introduce these round trip times that are, not great. There's a more pernicious thing though, which is that you've now introduced some concurrency between any sort of policy changes that you apply to this policy change oracle and any kind of application logic. And that's really, really difficult to keep in sync. It's even more difficult to keep in sync when you start to expect your policy change to take effect before some point in your pipeline. If you've ever encountered this problem, let's drink together. So the other issue, of course, is that your policy is non-composable. This is like a really trivial case. It's a global thing. By the way, it's a trivial case, but it's everywhere, right? Like access control lists are this. And if you've ever been tempted to call into some smart contract to authorize or to derive a set of permissions, then you have exactly this problem. And so it's non-composable because any kind of global policy change is going to affect absolutely everybody involved. And there's a last problem that typically it's called ambient authority. And this problem basically boils down to the fact that attackers are able to express operations on resources they don't have. The example I like with this is, there we go, is you can try to open. I'm being attacked. You can try to open Etsy password and just kind of see if you can. And this opens up a whole lot of vectors of attack that we'd like to rule out. Okay, so what do we need? We need some safe by default protocols. Here's my vague attempt at kind of setting up criteria for what that looks like. So they're secure. They don't leak authority. You're not going to give permission to anything implicitly. The way you achieve this is you're gonna try to isolate things so you can only interact with objects you've explicitly been granted. You're going to subject yourself to some sort of access control. Yeah, such as. Here we go. So you can, access control basically implies that even if you've explicitly been granted an object, you might not be able to do everything, and that can change. And then secure delegation, sort of the thing I'm angling at here is that when you delegate authority to someone, you want it to be exactly what you're designating and not anything to slip through the cracks. Then, of course, we want this to be deadlock-free and behave reasonably well in concurrent systems. So here's the solution. Here's a solution. Or at least elements of one. And I'm taking a little bit of a different approach on this. I'm going to look at the concurrency and networking side of this first. And for those of you who are familiar with OCAP, we'll merge back into the ambient authority stuff later in the presentation. So the solution to this, in my mind, really begins with the networking level and the concurrency control level. So we start with a system where we have three components. We have an object heap, which is on the right. We have a single stack. I'll explain what that means. And we have a single thread of execution. So the single thread of execution is exactly what it sounds like. The single stack is a way of saying that the system is not going to have suspendable coroutines. We're going to run one thing to completion and then the next thing to completion. The trick, though, is that these messages arriving over the network that we're handling through the event loop, the trick is they're being processed asynchronously. So they're carrying asynchronous message calls to some of these objects on the heap. The event loop is going to map them there and map the responses back to the callers. But from the caller's perspective, they're not blocking and waiting for a response. They are immediately returning and obtaining a promise, which will resolve down the road. This turns out to be irrelevant. The other thing is these objects that we are calling methods on, this is object-oriented programming, you designate them over the network using an unguessable reference. So it's going to be like a UUID, it can be a random uint64, it doesn't really much matter. But I really want you guys to think about this in terms of an event loop with an object model and an event loop that runs sequentially end-to-end, one event every single time with the small footnote that event is asynchronously called. Here's what I described in a little bit more detail. So this is where it starts to come together a little bit, hopefully. The asynchronous RPC has the main goal of avoiding deadlocks in the system. There's a nice property that emerges from this too, which is that sometimes you fall into this pattern where you want to call a method on one object, take the result of that object and pass it in as an argument to another method on the same object or on another object. And what we're able to do when we reason in this eventual send promise type environment is we're able to do something that looks like we're time traveling with the request flow. So what happens here is you make the first call to foo in the client. That reaches the server. Then you immediately make the call to bar from the same client. And what you pass in as an argument is the identifier of the promise that you've received back from the server for your first call. And so when the server receives your second call, it's able to look at your input argument and it's able to say, oh, I see. This is going to be the result of the first call. I already have that locally. I don't need to do a round trip. And so when you get enough of these things together and you start to scale this up to the level of the network. Oh, right. Sorry. I have another slide here, don't I? Yeah, so just a quick observation that I want to point out here is that this object graph and the references between these different objects, you can think of it as embedding directly into the peer-to-peer network, which becomes relevant later. Yeah. Boy, these are not in the order I thought they were in. Okay. I think I'm at 10 minutes here too, Dan. Can I have another two? Okay. All right. So right now I've showed you a mechanism by which I can share references to objects I can send messages to objects along references I hold to the objects. There's a really naive version of this. So Alice has a reference to Carol. These are code objects, and a reference to Bob. Oh man. Oh man. This is I've embraced all the messy. Hey. All right. So, um, yeah, I definitely want to get this point across. So there's sort of a naive way you can share references over the network, and this would be in this situation where we have Alice who has two references, one to an object Bob, one to an object Carol, um, and we call a method foo on Bob, so bob.foo, and we pass in a reference to Carol. There's a problem here, which is yeah, we got to decide when we were delegating authority and when we were composing Bob and Carol together, but Bob now has access to everything Carol can do, all her methods, and he has it forever. So we call this unattenuated composition, and I think it's quite obvious why this is not ideal. Attenuated composition is where it starts to get a little bit interesting. So what you can do here is you can have Alice create another object that we're going to call the caretaker. That caretaker holds an object holds a reference to Carol, which is what we ultimately want to pass Bob indirectly. And so what we then do is in our call to foo, instead of passing a reference directly to Carol, we pass a reference to the caretaker object, which itself has a reference to Carol. What this does is when Bob tries to call this caretaker object, the caretaker can run a check on a Boolean to see if it's still enabled. If it isn't, it just drops the message, and in this way, Alice is able to revoke this capability that she previously granted to Bob. And there's like equivalents for doing things like you can ignore certain messages on Carol, and that would be a means of attenuating that particular capability. And you can extend this pattern so that maybe the caretaker can only be called once and these kinds of things. All right. I'm taking one more minute. Returning briefly to the wetware project, what are we trying to do with this? This is where it gets super messy. It basically boils down to this command. You can do wetware run my binary. What it will do is it will run your binary in a fully jailed process that goes quite a bit beyond what you usually see in a container environment, because it sets things up so that there's only one possible way for the guest binary to communicate with the outside world, and that's through this kind of VAT network that we described here. When you do this, something kind of interesting happens, right? Well, okay, I'm going to stop taking extra time and I'm going to try to wrap this up a little bit. When you do this, when you eliminate every other means of discovering information or data on your network other than your shared reference graph, then something kind of interesting happens, which is that you've basically collapsed the ability to name something with the ability to use it. And because you are only capable of calling methods on objects that you have references to, you're no longer able to articulate an action that you're not allowed to take. So I'll let you sit with that for a little bit and kind of think through what that entails. And I'll skip the rest of my slides just to make this point. The kind of interesting thing that happens here is that there's an entire class of attack that gets essentially factored out. And these are attacks in which somebody who is allowed to do something does it on behalf of somebody who isn't. So if the person who isn't can no longer articulate what it is they want done because they don't hold the references that can encode that, then they can't ask a deputy to take an action for them that shouldn't happen. Okay, that's like 14 minutes. I promised 8. I'm not sorry. Goodbye.